For reviews, I'm going to start by just going through logistics. So the first thing is that, like I said in class, the exam will be roughly 10 to 12 questions. About a third are multiple choice conceptual questions, similar to what's on the quizzes or what's in the practice sections on Canvas. So practice chapter 1, chapter 2, and chapter 3. The remainder of the questions will be calculation based, so similar to some of the calculations we've seen in the notes, or similar to homework problems, but even more so similar to the questions in this review packet that I had posted a while back. So if you haven't looked at this yet, be sure to take a look at this, especially the equation sheet, because this is what you will be provided for the exam. It will look exactly like this unless I realize, oh man, I forgot an equation. But I usually don't take off equations unless I just don't think they'll help. So your first two pages should look like this, the wording and everything, except it'll say exam instead of practice. And like I was saying, the calculation part is going to be similar to some of the questions here. You notice there's not many chapter one because we really end up using trig throughout the rest of the chapters. And so this is just a quick little, uh, almost not even worth adding set of questions for chapter one because the real meat is in chapter two and three. So I think what I'll do is just start by going through some of the common mistakes I see for different types of problems. And so to do that, I'm going to just run through some of the notes. So I will just jump straight to chapter 2 because that's where we end up using a lot of these tools. So the first point where I usually start to see some mistakes happen is position time graphs. The main one being people forget how to find the average velocity. All you do is you find the slope. To find instantaneous velocity, all you do is find the slope, but at a single point. So I'll come over to my graph paper over here. If I have time over here, position over here, and my graph looks something like maybe that. And I ask you, all right, this is 1, 2, 3, 4, 5, 6, 7 seconds. And we'll just make this 1, 2, 3, 4 meters. If I ask you what is the velocity at 5 seconds, you might think I don't have enough information. I've only got 1 point, and slopes make me use 2 points. Well, this is a straight line, so the slope at that single point is the same as the slope between any 2 points. Two that might be convenient to use are these because they line up with the numbers. So this would be going from at time 4 seconds and position 2 meters up to at times 6 seconds, position 4 meters. The average velocity and instantaneous, because average is between two different points, instantaneous is at a single point, but both will give the same slope here. Both of those I can calculate as final minus initial, displacement over time. And so that'll be 4 meters minus 2 meters over 6 seconds minus 4 seconds. And that'll be 2 over 2. So 1 meter per second. It is positive, meaning it is in the positive direction. So what you also have to remember here is this does not mean I'm going, say, northeast or something. We've gotten pretty used to 2D at this point, and that can make this confusing to come back to. Remember, in 1D, you can only move either east or west, or north or south, whatever two directions you're allowed to move. So east is actually upward on the vertical axis, and west is downward. And this is just saying, on average, I'm moving upward over time. And this is where I said, if you're not sure, it can help to take your whole graph and just rotate it. And then it's a little bit clearer to see, okay, right means east. So in this first leg, I'm moving east. I'm not moving for this second leg because I'm not going east or west, left or right. Here again, I'm moving east. And then here I'm moving back to the west. And by the end of this trip, I actually end up back where I started at x equals 0. It just gets a little confusing because x is the vertical axis. We're used to it being the horizontal axis. All right, so that's position time graphs. I think that's the big stuff about them. Knowing velocity versus acceleration and how to tell if something's speeding up versus slowing down is a common conceptual issue. Remember, the only rule there is if velocity and acceleration agree, speeding up. If they disagree, they're in opposite directions, slowing down. There's nothing special about plus or minus. That alone does not tell you speeding up or slowing down. If both are plus and both are minus, that tells you speeding up. If one is plus and the other is minus, that tells you slowing down. So the real rule there is just same sign speeds up, opposite slows down. Calculation-wise, the biggest thing for the first chapter is kinematic equations, and it's the same procedure every time you do one of these. You just read through the problem, you highlight information you're given, and this is something that sounds obvious, but notice how I'm actually writing variables for these things. So it helps to know we use A for acceleration, T for time. In Physics 1, it's pretty easy because most things agree with what you'd think they'd be called until we get to things like momentum and we use P. But for now, at least, um, you could almost just guess what the variable is. And the reason I do that is not just to remind myself what I'm looking at, but because it's going to help me track down the right equation. The right equation must have these things in it. Or sometimes I need two equations. It's still going to need to have those things in it so I can relate them. And that helps me pick an equation. The table right here is just me helping you out with doing that, specifically for kinematics problems. So this table might be something good to have in a cheat sheet because I'll list the equations. I'm not going to list all this stuff. Okay, and then the other thing is watch out for hidden phrasing. So for instance, in this second problem, I said starting from rest. So you have to remember that means initial velocity is 0. I'm not going to outright say it sometimes, but that's your cue, that initial velocity is 0. Some other ones would be things like I tell you something is slowing down. You have to know that that means velocity and acceleration are in opposite directions. So I could say car is going to the east, but it's slowing down with an acceleration of a certain magnitude. So acceleration has a magnitude of 2 or something. You have to know that that actually means in your table, so when you're actually using it to calculate, you should really put A as -2, because if the car was moving to the east but slowing down, the acceleration is to the west, opposite the velocity. Okay? If you don't account for that negative, then you will probably get a wrong answer, if not make it really difficult to solve the problem because you're dealing with some square roots and negatives or something. Okay, so just watch out for word clues. If it feels like you don't have enough information, you do. You just have to read the problem more carefully. For free fall, by this point, usually most people have it hammered in their head that the acceleration is that. And so it's harder to trick you, which is good. But do remember that for free fall, things stop at the top. That's another cue. So if something asks about the maximum height, you know the velocity in free fall is 0, or vertical velocity only for projectile motion when we get there. So we saw something like that here. Max height automatically clues you in that this should be 0. It's not going to say it outright, but you need to know that. For chapter 3, this is where I'm really going to come over to my other sheet over here. The biggest problems are not so much with calculating, but all the stuff that comes before it for vector stuff. If I draw a couple random vectors, or I give you some information that should inform you about the vectors. So say I have vector A and I have vector B, and I ask you, what is A plus B? You have to know how to do that no matter what the orientation of the vectors is. So I'll use those in a second, but I'll draw maybe another A like this, and B is like that, or any random combination of vectors. And it again could be like I give you a picture like this, which is what we saw in the quiz, or I give you information about a trip someone took, like the bird watcher problem in the notes. So they went east, then south, then north to west. Regardless, you need to be able to draw the vectors first of all, and then add them. To add two vectors, the easiest way is to imagine yourself walking along the first one and then along the second one. And then the resultant, the sum of those two, is the shortcut you could have taken. So for instance, if I'm trying to find A plus B for these first two vectors, I imagine myself walking along A first, then walking along B. A plus B, the resultant, is the shortcut I could have taken. I could have, from my starting position, walked straight to the ending position. So this is A plus B. That's the shortcut I could have taken. The arrowhead goes to where I'm trying to get to, not where I'm coming from. I wouldn't say to get from the start of A to the end of B, I go this way. That would be to get back to my starting point. So be careful with your arrows. If I'm doing B plus A, I would walk along B. Picture myself doing that. Then picture myself walking along A. B plus A is the shortcut I could have taken from my starting point to the ending point. Now, for vector addition, I get the same thing whether I do A plus B or B plus A. Those are the same vector. For vector subtraction, the order is a little bit more important. So if I do, say, A minus B, again for these first two vectors, A minus B actually means A plus the flipped over version of B. So I imagine myself walking along A and then along the flipped over version of B. A minus B is the shortcut I could have taken instead. And B minus A, just do it real fast, is I imagine myself walking along B, walk opposite the direction of A. This is negative A. B minus A is the shortcut I could have taken. All right, and I'll just do all of those real fast for these two other A's and B's I could have worked with. So let's see, I'll do A plus B right here. I walk along A, and then I walk along B. A plus B is the shortcut I could have taken. All right, B plus A. I walk along B, then I walk along A. B plus A is the shortcut I could have taken. A minus B. I walk along A, then I walk along the flipped over version of B. So it's same size vector, but opposite direction. That's negative B. A minus B is the shortcut I could have taken. And finally, B minus A. I walk along B, then along the flipped over version of A. So negative a. B minus a is the shortcut. All right. So that's the first thing that comes up is just not drawing the vectors correctly. The second thing is dealing with components of vectors. So I'll just string some vectors together. So say you've already gotten through that first hurdle of someone's going on a trip and they go this way first. That's vector A. And then they go this way, and that's vector B. And then they go, I don't know, off over here, vector C. Their overall displacement, meaning the full trip they took, is just the shortcut. So out to there. That's A plus B plus C. But we a lot of times just call that the resultant or the overall displacement. Okay, so that's not too bad to do sketching it like that, but to actually get numbers for these things, that's where components come in. And so I'm going to sort of isolate A, B, and C so you can see this better. To draw the components correctly, what may help is to imagine your hand is only allowed to move left and right or up and down. And to see what I mean, I'll sketch in some axes that will say, okay, I can only move either this way, that's left to right, or I can move this way, up and down. Right here, I can either move this way or that way. And then right here, either this way or that way. This is kind of going in the reverse direction of saying, instead of looking at vector A, I could imagine what I'd have to do to get there by only walking east to west and north to south. Like I have to get from one building to another in a city, but I can only go along the city blocks and they're all rectangles. So I can't just cut a diagonal because I'd have to run through a building. So in that case, all right, I'm right here. I've got to get over here. I could do that by moving to the east and then moving to the north. So this is AX and AY. And automatically, this is going to be a right angle because the X and Y axes are always perpendicular to each other. I see wild things for the components of a vector, and it's because you end up allowing yourself to essentially draw whatever comes to mind. Make yourself follow this rule that your hand can only draw arrows that point left to right or up and down. You could think of something like this. You could think, oh, well, I could go this way, and then I could go that way. Those are some random vectors you just drew. You're not wrong. You could do that, and adding those two does give the blue vector, but that's not helping you do any math because those are also weird angles. The goal of components is to deal with angles that you're used to, 90-degree angles. And then we can use Pythagorean theorem, trig, and all those other useful things. Whereas with those odd angles I just drew, I'd have to know how to do that some other way, I guess. All right, similar for vector B. I'm only allowed to move left to right or up and down. Well, then to get from here to over here, I'd have to walk to the right and then walk down or east and south, depending on what kind of problem we're looking at. So that's BX, that's BY. I could also have walked to the south and then to the east. And then that is BY, that's BX. Depending on what angle you're given, one or the other is more convenient. If, say, this is a 30-degree angle and this is 60, it might be in the problem I'm given the 30-degree angle and not the 60. Okay, well, in that case, I would like to use this upper triangle, the one whose right angle is right there. In that case, BY is opposite the 30-degree angle, so I'd use sine. It's downward, so negative sine. And BX is adjacent, but it's to the right, so positive. B cosine. And right here, I need to say 30. On the other hand, if the problem gave me these 60-degree angles, now Bx is opposite that 60-degree angle. So I would calculate it as, it's still to the right, B sine 60. And then By, it's still negative, it's still downward, but it's adjacent to that 60-degree angle, so negative B cosine of 60. And this is the same vector I'm talking about, whether I use the 30 or 60-degree angle. And so you might look at this and say, I'm going to get two different answers. Well, if you put cosine 60 in your calculator and sine 30, those are the same number. So both of these are correct. Same for the bx's. All right, so just work with the angle you're given. Or, if you just hate 60-degree angles, if you remember that it'll add up with a different one to get 90, then you can just use the other angle, the one you like. All right, and last, for vector c, same deal. I could get from the starting point to the ending point by walking to the right and then walking upward, or walking east and then north, whatever the problem calls for. So the takeaway is be very careful when you draw your components. Don't draw some random ass lines and say, all right, there's my components, good to go, because that will make the whole rest of the problem wrong, and you will be very confused on what's going wrong because the things you're trying to do math with aren't mathing. Because you'll see this and you'll be like, well, is that a right angle? I don't know. What is this angle? How do I get this length? That's at a weird angle. It's not horizontal. And it's because you drew it, but you stick to that. You keep your drawing because you're like, that can't be it. And I'm saying this from just seeing it happen many times. So just be very careful drawing in components. The last thing for chapter 3 is we get into the projectile motion stuff. So we'll come back over here for that. So in addition to this kind of problem, which I've said a few times is definitely going to be the type of problem that would be on the exam, and it's what we were just talking about. Some of those things you need to make sure of with your drawing, adding the vectors correctly, and then finding components correctly. The other big calculation thing in chapter 3 is projectile motion. So things like these problems or the problems on the next page. The thing that people miss a lot for a projectile motion problem, if I happen to tell them, is if I tell you something's launched horizontally, automatically you can say, okay, then the vertical velocity is 0 initially. And that's another one of those kind of hidden phrases that's still telling you something. The other hidden phrases are ones you'd already recognize from free fall, and that would be things like maximum height. But again, that now means that this is 0. It does not mean that Vx is 0. Vx stays the same throughout the whole flight of the projectile. So in projectile motion, maximum height just means vertical velocity is 0, not the overall. The other thing people forget is that they can automatically fill in the accelerations in projectile motion and free fall. And the final thing that people mess up with these is if I give you the speed of the ball, I can't put 22 right here. I guess the initial would be where I'd try to put it. I can't do that because then I'd be saying, all right, it's launched at 22 meters per second to the right and 22 meters per second upward. No, because then the overall speed would actually be faster than 22 because it's going this way at 22 and this way at 22. That means it's actually moving along a diagonal at 22 and some change. It's 22 square root of 2 if you want to do the math. But anyway, takeaway is this is not immediately telling you what goes in these slots. It is telling you, okay, take this number, see how much of it is in the horizontal direction and how much of it is in the vertical direction by using that angle. With this, you usually can say the x component's going to use cosine because it's very typical to specify the launch angle as angle from horizontal. We don't typically specify that kind of angle using this. So for projectile motion specifically, it's okay to just say X component is cosine, Y is sine. But remember, the general rule is X is adjacent. I'm sorry, cosine is adjacent and sine is opposite. That's the only rule you've got is any components that are adjacent to the angle, use cosine. Any components that are opposite, use sine. And that's, I think, the main gotchas. The rest is just getting used to doing these types of problems, and that really comes with practice. There's not words I can say that'll help hammer that in. So, are there any questions?
I did have a question, which was like you said that we could use like a take a sheet. I kind of want you to specify a little bit about that.
Okay. So 8.5 by 11, normal sheet of paper. I'm not going to bring a ruler, but I'm just saying I don't want to see a poster board. Whatever you want to put on that sheet of paper is fine with me. I would recommend putting certain things, such as the procedure that we use to add vectors. So this page right here, a condensed version of that, maybe an example of it. Maybe things like your check marks for projectile motion and how you apply that stuff. And then the other bit of advice is don't try and cram a million example problems into your sheet because I can always come up with something that's just a little bit different from all those. And so what you really want to get out of that sheet is a process or a procedure for solving problems that's going to work no matter what little things I do to trip you up. And that again becomes more clear with practice. If you do enough projectile motion problems, you realize you're doing the same thing every time. There's little variations, but the procedure's the same, and that can be what's helpful to remind yourself of on the cheat sheet. But anyway, one sheet of paper, 8.5 by 11, whatever you want to put on one singular side of that sheet of paper. I'm looking at some emails I've gotten. So this first email says, what specific terms do I need to review for the exam? I don't really test on terms, so I'm not going to ask what is free fall or what is projectile motion. It's more about applying ideas, and that's what makes it difficult compared to probably some of the other courses you've had to take, like anatomy might, I don't know if you've had to take that, but it requires lots of memorization. It's just staring at a sheet of paper with all the labels for an hour and then, putting that away and trying to remember it, trying to write it down, or using flashcards or whatever. That does not work for physics because you're not memorizing, you're reasoning from the information you're given. And if you try and go at it as if it's a memorization class, it will really screw you over because you won't remember the right things for the specific situation you're looking at. That's why practice problems are the best way to prepare because they throw you into the deep end of lots of different variations and you just kind of get used to the procedure and the little changes between different problems don't trip you up as much then. If you're memorizing, you're not going to find the exact right problem in your memory bank or on your cheat sheet. The second question was, are there specific problems from our notes, quizzes, or homework that would be beneficial to look over? I think I addressed that. I would focus on notes type problems and the practice questions more so than homework because homework can tend to be a little bit harder. And also the Wiley questions are what they are. So it's a toss up there. Quizzes are good for preparing for the conceptual stuff because I do ask variations on a lot of those questions a lot of the time. And then the last question was, what is the most important section from each chapter to review? I think I addressed that. Any other questions popping up in the meantime?
Could you rework number 41 on the practice exam?
Sure. Let me go to a fresh version. Okay. So City A lies 30 kilometers south of City B. We start at City A, travel this way to reach City C. How do we get from City C to City B? So I'm going to draw in some north, south, east, and west axes. And since it says beginning at city A, I usually like to take the origin as wherever I started this whole problem. So this is city A for me. Okay, that is 30 kilometers south of city B. That means city B is actually up here because A is south of it. And the last bit is from city A, the bus travels 50 kilometers at 37 degrees north of east. So this was 30 kilometers from right there. And then the bus actually goes 50 kilometers, 37 degrees north of east. And I'm just kind of guessing on this. I don't know that that's the right length or right angle. I'm just sketching. So 50 kilometers, 37 degrees north of east takes us to city C. The question is, what does the bus have to do to get from city C to city B? So its goal is to get from here to over there. And this makes it look like they just have to drive due west. I don't want to assume that's true because, again, my drawing might be a little off. So I'm just going to see where the math takes me, but I should get something that kind of is similar to this if I drew things roughly to scale. Okay, so the question is, how do I do that? Well, this I could look at as I actually want to get from A to B. So I want to go up there by the end of all of this. But what I actually end up doing to get there is going along this vector, I'll call it A, and then going along this vector, and I'll call it B. But I can see from the labels I drew, going along A and then along B is equivalent to the shortcut I could have taken, going straight from A to B. And I'll give that last shortcut a name. I'll just call it C. This helps me set up a vector equation that says A plus B will take me to the same place that walking along C would have. But I'm looking for B. I don't know what B has to be in order to get to C, which is a tongue twister. But this equation, it kind of lets me do some algebra. It says, okay, B is equal to C minus A. I just moved A over to the other side, but I just have to remember this is what vector subtraction means. You flip A over and then you add it to C. Once I've figured this piece out, the rest works pretty much exactly like we do everything with components. So I'll make a table. Oh, sorry, not force, vector. We haven't gotten to forces yet in this stuff. So here I want to work with C and negative A in order to get B. But other than that, it is the same as any other vector addition problem. So components of C would be I don't move left or right. I do move 30 kilometers north. For vector negative A, I got to be a little careful. Negative A is A flipped over. And so it actually points down and to the left. And so that would be my two components. You could also just say they're going to be opposite what the components for A would be. And it points to the right and up. So the flipped version of that will point to the left and down. And it'll be A. From here, I can just go back to looking at my original picture because the lengths of these two sides will be the same. They're just flipped over. So the X component is A cosine 37. The Y component is A sine 37. And so that'll go here and here. And A itself, the magnitude or length of this vector is 50 kilometers. But once I get to this point, it's pretty much just like any other vector addition problem. I add down the columns. I don't have to subtract because I already took care of that by using negative A. And then I'll get some numbers here. Those numbers correspond to the x component of vector B and the y component. And then I can do Pythagorean theorem to figure out the distance or size of the displacement that I need. And then I can do trig to figure out the direction, again, as usual. Is that okay? Is that enough? Or do you want me to keep going through it?
No, that makes sense. I just needed to know how to start it in the first place.
Okay, yeah, no problem. And I may have done this differently in the practice, and that may have made it more confusing. Let me see how I did this.
I think it was like vector AB, vector BC, and I think it just
Okay,
confused me or something.
okay. So what may help, the stuff I drew on the left is just another way to add these things. Really, all you need is the picture on the right, which is what I drew in the version I just did. So that extra stuff I drew in was just to show, okay, CB is AC minus AB, or AB minus AC. It was just kind of checking my work, but the picture on the right is the actual important bit. Okay, got a couple more over email. They were 23, 30, and 42. So I'll jump over to 23. Truck passes a car as it starts from rest. How much time does the car take to catch up to the truck? I guess the idea at the time was if you can do that, you can do any kinematics thing I'll throw at you. They will be easier than this one. Anyway, a truck is going 15 meters per second and it passes a car, which I'm just going to draw a parallel track for that. It starts from rest. The truck travels at constant velocity. The car accelerates at 3 meters per second per second. So this one has 0 acceleration. Maybe I'll start adding some labels. So this is V initial truck, A truck, V initial car, and A car. How long does it take for the car to catch up to the truck? So the car is going to catch up because it will gain 3 meters per second of speed each second. Catching up means they're at the same position at the same time. So the question is, at what time? Does the position of the truck, so X truck, equal the position of the car? From here, it's just a problem of how do we write these in terms of those accelerations and velocities we were given. Well, X truck is going to be V initial truck times time plus 1/2 AT squared. So kinematics for the truck, but it's not accelerating. So I actually didn't need this second term. It's really just this stuff right here. And then for the car, very similar there. It's just the car values. And so I really just have to say, all right, when does this equal this? So at what time t does that happen? And that is a quadratic equation, but I could be a little sneaky and rewrite this as 0 equals this minus that t plus 1/2 a t squared. I can factor out a t. And plus 1/2 a c t. And then that's two different options. If either thing equals 0, then the product will equal 0. So it's either at t equals 0, they're at the same position, which, duh, because that was the starting position for both. So that's not what I'm looking for. I'm really looking for this second case, v0c minus v0t plus 1/2 a t equals 0, and you can solve that for time. Okay. Let me come over here, see if that's roughly how my brain did this the first time. Oh yeah, I forgot that the truck started from, or the car started from rest. So I could have thrown out that V0C, but otherwise I did do it the same. And what you'll notice too is, in addition to my picture being much nicer here because I took more time to draw it, I used slightly different labels for things. I just called it 1 and 2, and I still, got the right answer. So there's nothing sacred about what labels you use. It's just if you at least use similar ones to what we use in class, it'll help you spot the right equations. Um, the other thing is that I drew a picture, period. Like if you just scroll through this, you will see lots of pictures. And really for things like this one for 17, I should have drawn a picture. I got lazy because I got tired of doing all of these kinematics problems. But you should draw pictures everywhere you can because they'll help you answer this in a way that kind of tracks. Like if what your numbers are saying is wildly different from your picture, usually it's your numbers that are wrong, not the picture. But I was also asked about 30. Okay. He throws a tennis ball vertically upward, returns after 3.5 seconds. So here is him throwing a ball straight up. It'll fall back down and reaches that same height after 3.5 seconds. How fast did he throw it? So what was the speed of the ball as it was released? I'd call that V initial. This is a 1D problem, so I could just leave it there. Or if you're like, I don't know if that's 1D or 2D, you might call it V0Y, but nothing's going on in the X direction. So I'm just going to leave it at V0. Okay, so it's a kinematics problem. The question is, what is the speed? I know acceleration automatically because it's free fall. I know the time because it's given. I don't know the final velocity. There is a way to know if you're clever, but it's not strictly given. What is strictly given is that the ball returns to the point of release. That means overall it had a displacement of 0. Yes, it went up, but it also fell back down, and it ended up back where it started. So 0 displacement overall. Kinematics says I might pick this one, because that relates all the things I'm given, what I want, and not what I'm not given. But in this case, the question is, what is V0? So to solve for that is not quite as bad. It's that displacement, which is 0 anyway, minus 1/2 AT squared all over T. So that's minus 1/2, negative 9.8. T is 3.5 all over 3.5. I could have simplified before doing it, but 6 in one hand, half a dozen in the other. which I've learned is not maybe a common saying, and I thought it was. So if you're wondering about that, it means same difference. I get about 17 meters per second, 17.2. And I'll just check myself. Yeah, 17. I did it slightly different here, but same answer. And the other thing I could do is actually I can do this without much math. So takes the ball 3.5 seconds to go up and come back down. Because that's symmetric, the time it takes to go up is the same as the time it takes to go back down. Each is half of that total time. In other words, it takes about 1.75 seconds to go up, 1.75 seconds to come back down. Well, 1.75 seconds is also the time it takes for the speed of the ball to go from V initial to 0, because it's going to stop momentarily at the top of that path. So I could word this question as, what speed does it take that if you throw something upward, 1.75 seconds later, it will reach the top of its path, it will come to a stop? Well, we know acceleration subtracts off about 10 per second. So we're looking for a speed that if you subtract 10 off it each second that passes, and you do that over 1.75 seconds, you will get 0. And the answer to that is 17.5 meters per second. So after 1 second has passed, the ball will be going that minus 10, so about 7.5. Another second is a little bit too much because that would subtract off 10. That won't be at the max height. That'll be when it started falling back down somewhere over here. So this will go to 0 after 3/4 of a second, roughly, because it's 3/4 of 10. So 17.5 is my guesstimate answer. The actual was 17.2, so pretty close. Um, Things like that are just a good sanity check to make sure you didn't say it'll take a year for the ball to come back down or something. The last one someone asked about over email was 42. So this one is 2D motion, but it is not projectile motion. So the stuff we said about 2D motion still applies. This is like talking about that ship that's going up and to the right. Um, and in this case, it's not the usual AX is 0 and AY is -9.8 that we see for projectiles, because this isn't a projectile, it's a puck. I guess it's like air hockey or something. But in all other ways, this is the same type of problem. So let me sketch this. Okay, so at time 0, a puck is sliding on a horizontal table with a velocity 3.6 meters per second, 35 degrees above the x-axis. So it's sliding 3.6 meters per second, and it is 35 degrees above the x-axis, meaning the horizontal axis. As the puck slides, a constant acceleration acts on it so that it has components AX and AY as given. AX is to the left. AY is downward. So we can really just read this as the puck is going to slow down as it slides. I would guess what's causing this constant acceleration is friction with the table. The question is, what is the velocity at 1.5 seconds? So I have to think carefully about what variables are being given to me. This is V initial, the overall velocity vector, not the x and y components of it. Similarly, they ask about the velocity. So they want final velocity, not just the x and y components. But I can still treat this as two separate kinematics problems. V0x, Vx, Ax, t. and then y, v0y, vy, ay, and t. So they don't say a thing about how far the puck slides in the x or y directions. They do say it takes 1.5 seconds, and that's the time it takes for the vertical and horizontal motions. That's why I can put it in both. They also give me AX, it's negative 0.36. I'll leave out units for space. And AY, even leaving out units, I don't have space, but negative 0.98. And they give me, again, initial velocity overall. This is a lot like being given the launch speed and launch angle. I have to break it into pieces. So I'll just kind of blow up that velocity vector so you can see what I'm doing a little bit clearer. I mean, I'm just zooming in on that. This is my high-tech way of showing I'm zooming in. So this is the overall initial velocity, v0. v0x is how fast the puck is sliding to the right initially. v0y is how fast it's sliding upwards. And this angle is 35 degrees. So v0x would be v0 cosine of 35 degrees. It's adjacent. v0y is v0 sine of 35 degrees. And give me a second to calculate those. So v0 is 3.6. That's what's given at the top. So v0y is positive 2.06. And v0x is positive 2.95. And so those can go down here. Again, leaving out units just for space, 2.06. Okay, and the final question is what is the velocity, meaning overall? And that's going to require me to give a magnitude for it and a direction. But I just have to remember that to get the magnitude, you just put together the x and y components. So that magnitude is the same as that. And in my picture to show what I mean, a little bit later, we said the puck will be a little bit slower. So maybe it's moved off to like over here or something. And it's not going quite as fast. And I don't know, it might be at a slightly different angle, something like that. That's the final velocity. That has an x component, vx, and a y component, vy. And here's your high-tech zoom of that. Vx is how fast the puck is sliding at the end of this whole thing horizontally. Vy is how fast it's sliding vertically. And probably I should scooch that over so it actually ends up adding up to give that overall velocity vector v. Maybe something more like that. And theta, with all the room I've left myself, is that little angle in there. That's what I want to find. Okay. The takeaway is as long as I can find Vx and Vy, I'm pretty much done. Because then I just say, okay, well, the overall is that, and the angle is inverse tangent of Vy over Vx. Again, ignore the signs. So this is really asking, how do I find Vx and Vy? Well, that's just two kinematics problems, one for the x and one for the y. The kinematic equation that will work best for this is Vx equals V0x plus AXT. And then over here, Vy is V0y plus AYT. I'll use that to get a number for each, throw those numbers into here and here, and then I'm done. So it is very similar to projectile motion. It's just you're given accelerations here instead of assuming the usual 0 and negative 9.8. Everything else is very similar to what you typically see for a projectile motion problem. Okay, other questions? Well, going once. Going twice. Three times. All right. Well, if there aren't any other questions, we will close off the review there. I'll see y'all on Thursday. If you do have any questions pop up in the meantime, feel free to email me. I'll get back to you as fast as I can. And other than that, happy studying. Feel free to come in during office hours tomorrow if you want to meet in person. And I'll see you on Thursday.